The following quick quiz uses a Crookes tube that we're going to energize using a high voltage coil. Both can be rather dangerous. I have decades of experience with this and some expertise in radiation. Do not replicate anything that you see on this video. Just watch and enjoy. For today's quiz, we're simply asking about a magnetic field and an electron. This is a bar magnet north and south. If I set it like this and I simply shot an electron through that magnetic field, what would happen? That's our question. Let me show you the quiz. I'll hold it up right now. And notice the little E with a negative, that's an electron. As always, mark your answer as thoroughly as possible and list your level of confidence. Typical student responses are, wait, are you actually going to do this? Electrons really aren't real, are they? And even if they were, you can't see them. I'll say, don't worry about it, but yeah, we're going to do something like this. So try your best. At that point, they'll say, well, I know that north is kind of like a positive and south is like a negative. And if an electron is negative, it's going to end up wanting to go to the more positive north. So it's going to bend towards it. Others will say, no, north and south are poles and charges are different. They're not the same thing. Some will say, we learned about a right-hand rule with a thumb, something about the curling of your fingers for the magnetic field, but this is an electron, so maybe it would be backwards, but I really don't know. So those are the typical responses that we get. All right, the students really want to know if we're going to do something like this. And the answer is yes. And the way that we can do this is we can use an old Crookes tube. Now, these are old gizmos. I'm not sure if they still make them. This one's very old. I imagine this is 50, 60 years old. It's been sitting around forever. But you'll have a cathode, and that is this little plate right here, this flat plate. When you excite the electrons off of here, they end up going perpendicular. They're going to go to the anode. The anode's broken on this side, but regardless, we have electrons that are going to be streaming across. And I get you can't see electrons, but there's a little bit of gas in here, very small, intermediate to maybe even a hard vacuum, very temperamental. Regardless, they sealed these, we'll assume that it still works. The electrons can be blocked by this piece of metal. There's a little slit there. So only a stream of electrons are going to go to the anode. Now we can't see them, but I don't know if the camera picks it up, but there's almost a yellow tint on this piece of metal. And I think that's like a zinc sulfide or some other mineral that happens to fluoresce. That's going to allow us to see some of these electrons as they end up smashing into a few gas molecules, maybe some of that zinc sulfide, maybe they turn into a gas. Regardless, we'll be able to see a little bit of fluorescence here. And so we'll say that's going to indicate our electron flow. So to explain this, normally with the right-hand rule, I do it this way. Before we did, the fingers curl around showing the magnetic field on a wire if I have conventional current or positive flow. Well, for electrons, we'll simply use the left hand. Let's go back to the right hand for a second. This is the second right-hand rule. Again, we'll have our magnetic field and the fingers point from north to south. So if I had north to south here, and then if I had positives going this way, if I had north to south this way, the positives would end up going or be deflected down. See, the force comes out of the palm like you're giving a high five. That's the right-hand rule I use. We're going to end up using electrons, which would be the left-hand rule, which everything's the same. The direction of the electron, the magnetic field from north to south, and then the force shows what the electron would end up feeling like. I have this set up over in a vent hood over there to provide some shielding. So let's take a walk over there. All right, here's my vent shield, and I have an extension cord, and I'll be standing all the way over there. Why? Well, I have some background in this. I actually did a master's in X-ray crystallography. This is my thesis. I do want to point out something because sometimes people talk about the good old days. When you look at this thesis, you'll notice that there's going to be a bunch of pictures and things of that nature in here. You got to realize at the time we didn't have Google Image where you could just take the images and put them on here. we had to make everything on our own. It was really a pain. So you really have it made today if you're doing something like this, because, man, this took a lot of time. But regardless, what I'm telling you is I think that we're going to need to be standing over there, because anytime you take high-speed electrons and smack them into anything, especially metal, there's potential for some X-rays. So I'm going to stand all the way over there. And by the way, I understand that X-rays attenuate very quickly in air. I also have some metal here. I'll be standing way over there, so I should be fine. But to measure the amount of radiation given off, I do have a radiation sensor set up here, and then I can plug that in. You'll hear it starting to beep right away as I turn it on, just picking up background information. I have a camera here so we can see it. In fact, I'll move in here and show you the rest. Here's a look inside the vent hood. You'll notice that I've got an induction coil touching this piece of metal, which goes to our flat plate, and the electrons will come off in parallel lines that are going to be perpendicular to that plate. Most of them are going to be filtered out by that little metal slit, so only a few will go through there, and they'll eventually go over to the cold water pipe, which will act like ground. My magnet here, that says north, so south is behind there. So look, if I've got my electrons, and I'm using my left hand, electrons going in that direction, the field north to south this way, and the force would be down that way. So that's what we should end up seeing. We should end up seeing our electrons bending down once they hit that field. I'm going to hit the lights, turn on my sensor, and record this. All right, I'm going to plug this in. Okay, you can see there is a massive amount of radiation being given off. The scale that this has right now doesn't even show any of the background, so that is a significant amount of radiation. What an interesting phenomenon. You could see the electron beam is being bent down. But that's not the most interesting part. I decided to take the magnet off and get a shot of the beam going straight without the deflection. And when I did this again, this is what I saw. I hope everyone just caught that. The computer screen was shutting off. The electronics were getting irradiated and literally were shutting off temporarily and coming back on. I did this twice, each time it happened. So there's quite a bit of radiation coming off there. So I'm going to investigate a little further here. All right, you can see that I now have my sensor. I've pulled down the screen, and I have a big chunk of steel right here, and I'm going to lean right against here, and I'll try this again. All right, that cut it down by about half. All right, that was interesting indeed. First of all, we saw that without a magnet, you'll end up having the beam going straight across. But it appears that we are probably in the X-ray territory. When we think about the gas that's in here and getting close to a hard vacuum and the voltage that we're using, you know, tens of thousands of volts, we're probably in X-ray territory. The Vernier manual actually says that this detector can pick those up. Can also pick up gamma, alpha, and beta. But right away, the alpha and the beta would be stopped by this metal pretty quickly. In fact, the alpha completely, beta probably the same. But X-rays will penetrate steel, even of this thickness. So I would say that this is not something that classroom teachers should do. It appears that we're generating X-rays, and one of the fun things was it forced me to go back through some of the experiments that I had done before and look at some of the references. But when I was using 1.514 angstroms on a copper plate using a Brooker machine, we knew that the attenuation rate was just in centimeters. In other words, air itself would decrease the intensity of those X-rays drastically. So I was about 5 meters away, so hundreds of centimeters away. The attenuation from the air and just the inverse squared law is pretty much going to keep me safe. And when I took the sensor back to where I was standing, I picked up just background radiation and nothing else. So there's probably no danger to me at this point. But if you don't have expertise, I certainly wouldn't use one of these Crookes tubes in your classroom, especially the way that I've set it up. Maybe there's kits to do this. And I'm sure there's going to be some old school retired physics people that will say, you know, we used to do this all the time in class. Well, we used to let kids play with mercury too, and it's just out of fashion. So I would say, let's just watch the video. We don't need to reproduce this. Certainly interesting. I had a good time today, especially going back through the literature. But a magnetic field will definitely bend charged particles as they're flowing, and without it, they go in a straight line. Got to see some really interesting phenomena here. All right, that's your quiz for today. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe, and if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.